sliding filament theory. What is this sliding filament theory means? First we should understand what is this actin. So here suppose if we are having actin myofilament, this is our actin. So here we'll be having tropomyosin. Here we'll be having tropomyosin. Here we'll be having troponin. Here we'll be having troponin, and this line is called tropomyosin. These ring-like structures are called as actin. So this completely actin. Myosin is the thick filament. Myosin is the thick filament. Here we'll be having globular head portions of the myosin. Globular head portions of the myosin. Okay. What is this sliding filament theory means? It is nothing but the contraction. It is nothing but the contraction of muscle. It is nothing but contraction of the muscle. So that how this contraction will happen, that is nothing but sliding filament theory. Now suppose we want to do elbow flexion. Suppose we want to do elbow flexion. Elbow flexion we should do. So what is the muscle responsible for elbow flexion? Biceps brachii. Biceps brachii. So what is the nerve supply for this biceps brachii? Musculocutaneous nerve. So what is the root value of this musculocutaneous nerve? Root value will be C5, C6 and C7. This is the root value of the musculocutaneous nerve. From where all these things are coming? From spinal cord. Spinal cord is connected to the brain. Okay. Understand the point here. If we want to do elbow flexion, responsible muscle is biceps brachii, supplied by the musculocutaneous nerve, and the root value for the musculocutaneous nerve C5, C6 and C7. These nerve roots are coming from the spinal cord. Finally, spinal cord is connected to the brain. So what is the connection between this elbow flexion and brain? Means elbow flexion is nothing but the voluntary movement. That means we can control this movement. We will only give instruction to the muscles to do the movement. So here we means who? Brain. So that here brain will give instruction to the muscle. To do this elbow flexion movement. Brain will give instruction to the biceps brachii muscle to do the elbow flexion movement. How it will give instruction? It will give instruction from the spinal cord. First brain will give instruction to the spinal cord. That is because of one nerve. That is because of one response, that is motor response or motor system. Brain will give motor signals to the spinal cord. From spinal cord all these motor signals will enter into this nerve roots C5, C6 and C7. So from spinal cord these motor signals will come to the spinal nerve roots. From these nerve roots it will enter into the musculocutaneous nerve. From this nerve root it will enter into the musculocutaneous nerve. Suppose if we take muscle, the muscle will be supplied by the nerve fibers. So from this musculocutaneous nerve, these signals will come to the biceps. Suppose this is biceps muscle, this is musculocutaneous nerve. So these impulses from brain, it will come to the musculocutaneous nerve. From musculocutaneous nerve, these are the branches of the musculocutaneous nerve. These are going to give connection to these are connected to the muscle, biceps muscle. The point where the nerve is going to connect to the muscle is nothing but neuromuscular junction. So these are going to connect to the muscle. From here the nerve will give signals. Or impulses to the muscle. So then the muscle will contract. And it will do flexion. How the muscle will contract, that we will see in sliding filament theory. Clear? This is about sliding filament theory. Will go in very easy way. So here this is our muscle fiber. See this muscle fiber 1, muscle fiber 2, muscle fiber 3. So here we will be having 3 muscle fibers in one muscle. See, one muscle fiber we have elaborated like this. So here if we want to do movement, first we need a signal. That is nothing but action potential that will come through the nerve. So this is action potential. From there it came to the muscle. This is the nerve. So now when it is connected to muscle, this is neuromuscular junction. Okay, from here we got signals from the brain. So what this nerve will do, it is going to create the calcium. It is going to create the calcium inside the muscle. It is going to create calcium. It is going to release the calcium inside the muscle. Okay, first point, it is going to release the calcium inside the muscle. Okay, stop there. Now we come to actin. See, this is our actin. In this actin, if we observe in this actin, we will be having binding sites on the actin, and at the same time here we will be having troponin molecule. See here, this is our troponin molecule, troponin. This is troponin molecule. And here one more thing, tropomyosin is going to cover the tropomyosin is going to see here binding sites are there, no? Usually when the muscle is in resting position, tropomyosin is going to cover the all the binding sites, is going to cover the all the binding sites. Here also all the binding sites are covered by the tropomyosin is going to hide the all the binding sites of actin, all the binding sites of actin. So this is second point. Okay, remember. Now we'll come to the point. See, when calcium is released here, when calcium is released inside the muscle, that calcium will come and it will attach to the troponin. See, it will attach to the troponin. This is calcium. It will attach to the troponin. Because of this calcium attachment to the troponin, the here tropomyosin is there. No, this tropomyosin is going to show the binding sites of the actin. This tropomyosin is going to move upward. This tropomyosin will move upward so that these binding sites will be visible. These binding sites on the actin will be visible. These binding sites on the actin will be visible. So that this is third point. See, first point here, it will release calcium. Second point, what we discussed, binding sites on the actin will be covered by the tropomyosin. Third point, when calcium is released, it will attach to the tropomyosin. Because of that, movement will happen in the actin, so that this tropomyosin is going to show the binding sites of the actin. So now these binding sites are visible. This is third point. Now what is the fourth point? Means when these binding sites are visible, when suppose here we'll take, okay, when these binding sites are visible, the head, this is myosin. The heads of the myosin will attach to the binding sites of the actin. Heads of the myosin will attach to the binding sites of the actin. The place where the myosin head is attaching to the actin is nothing but cross bridge formation. So this is nothing but cross bridge formation. This is fourth point. After that, what will happen? Fifth point. After this cross bridge formation, the myosin heads are going to move in this direction. They will slide in this direction. If they slide in this direction, the actin filament will move in this direction. Suppose one myosin filament is there. Here one actin is there. Here also suppose cross bridges are formed. If these myosin heads are moving in this direction, the two actin molecules, two actin proteins, it will move in this direction. Here we'll be having jet line. Here we'll be having jet band. So how I am saying this? See, this thick myosin is here. This is thick myosin. These are thin filament. Thin actin will be here. Actin will be connected to the jet band. So here jet band is there. So one more actin. Between these two will be having myosin. This is our jet band. When it is moving in this direction, the length of the sarcomere will come. The length of the sarcomere will reduce. So same like this, how it's happening in one sarcomere. Same all the sarcomeres in muscle fibers will happen the same mechanism. Because of that, the length of the muscle will decrease. That is nothing but the contraction of the muscle. This is sliding filament theory. It will slide. Head of the myosin will attach to the actin, then it will slide the actin filament.